everyone. This is Dr. S. Chinnavenkateswarlu, working as a professor of EC at IRA, Hyderabad. Today we are discussing about filter design by Kaiser Window. So we know that all this all filters, we are talking about that digital filter. We know that all. With reference to that digital filter, the filter designed by Kaiser Window. Normally we know that all number of windows, like this is the popular window, Kaiser window. Previously we had learned that Gaussian window, Dahl-Seveshi window, and other windows, variable and fixed windows. But here we are going to design the filters by using this particular window, that is going to be the Kaiser window. So mathematically it is followed by that W of n is equal to I naught of beta of 1 minus n minus alpha by alpha square whole power of 1 by 2 by I naught of beta. So here 0 less than or equal to n less than or equal to capital M. Here this all we know, where n was small n value and m value. Okay, so here with this, where delta omega equal to omega s minus omega p, where a is equal to that a value, where a is equal to minus 20 into log base 10 delta. Okay, so here with this, where beta we don't know that one, beta we write consider that a beta, where beta is equal to 0.5842 of initial 0.1102 of a minus 8.7. okay, with where b is equal to, where that beta value 0.5845 of a minus 21 of power 0.4 plus 0.07886 of a minus 21, where here if you are considering this value, where a greater than or equal to 50, if you are considering this value where 21 less than or equal to a less than 50, okay, if the 0.0 a less than or equal to 25. Similarly, that m value, so that m value I need to decide where m is equal to, what do you call that, m is equal to a minus 8 by 2.285, what you call delta omega plus or minus 2. So after using these all values, graphically we write to observe that our response, where samples, number of samples versus what do you call amplitude. So where x-axis is the sample, number of samples. So from here it is mentioned here 0, 5, 10, 15 and 20. These are the number of samples are increasing here. The time in terms of the amplitude. So if m is equal to, capital M is equal to, here it is initially that order we have observed that one where m is equal to 10, 5 and 15 and so on. But here especially this, our case is where m is 20. The time where beta is equal to 0, beta is equal to what you call minus 3, beta is equal to 3 or beta equal to 6 and so on. We have to expect this output response after designing this Kaiser window filter design. Okay, with this best example of this, the Kaiser window design of the low pass filter. So use this all specifications where graphical representation. So after that, where h of n is equal to sine omega c of n minus alpha, I naught of beta of 1 minus n minus alpha by alpha square whole power 1 by 2 by I naught into beta. Here also same condition, 0 less than or equal to n less than or equal to m, we know that. So with this where 0 otherwise, where alpha is equal to m by 2, where m is already it is calculated, but here it is where alpha is equal to m by 2, it is also equal to 18.5. okay, so with this, that beta value, we are considering the same values. Here it is the beta value. Based on the beta value, m is ready to identify a value and what you call a greater than or equal to 50, 21 less than or equal to a less than 50 and a less than 21. like this, the Kaiser window design of low pass filter will appear. Okay, where that A is equal to minus 20 into log base 10 delta into delta of omega equal to omega s by omega p. Yeah, next example, based on that same example, we have to follow this step by step procedure for designing the Kaiser window design of the low pass filter. Here it is 0. So what do you call that? 0.99. Okay, less than or equal to that h into e power j omega. Okay, you know this all up with the mod. Okay, the mod less than or equal to 1.1.01. If you are ready to substitute that all omega, that this particular value is reflected where that mod omega is equal to what you call is less than or equal to 0.4 pi. Yeah, if it is what you call h into e power j omega, okay, omega with what you call that mod, okay. So that means that based on this value, it is less than or equal to 0.001, okay, with the condition based with the range as 0.6 pi. So less than or equal to that omega mod less than or equal to pi, with using this 0.99 less than or equal to h into e power j omega and h into e power j omega less than or equal to 0.001. So based on this, you have to follow these all steps. Step 1. So consider the step 1 is where the omega p equal to 0.4 pi, where omega s is equal to 0.6 pi. Okay, delta 1 is equal to 0.01, delta 2 is equal to 0.001, and delta is equal to minimum of delta 1 comma delta 2 is equal to 0.001. So like this, by using this all step 1, okay, so with reference to this all step 1, so directly write what are the omega value and omega s, delta 1, delta 2 and delta value is ready to investigate here. We are ready to assign these all values. Now coming to the second step number 2. So cutoff frequency, it is followed by omega c is equal to omega s plus omega p by 2 is also equal to 0.5 pi. Okay, so with this, so now coming to this step number 3, delta omega is equal to omega s minus omega p is equal to 0.2 pi, where that a is equal to minus 20 log base 10 delta is equal to 60. Where beta is ready to substitute here 0.5653, where m is equal to what do you call 37. Okay, so if you are missing this, where a value, that a is equal to what do you call the way a value is ready to substitute 0 log base 10 delta is equal to 60. If you are using that, a is equal to minus 20 log base 10 delta is equal to 60. The time where that value is where m is ready to substitute, that m is equal to 37. It is related to the step number 3. So for designing this Kaiser window design of a low pass filter, we have to follow this step by step procedure. After that, to write to design, we will expect your desirability. Step number 3. Under step number 3, where delta omega is equal to omega s minus omega p is equal to 0.2 pi. Okay, the time where a is equal to minus 20 into log base 10 and delta is, where here delta is equal to 60. So where m is ready to calculate a minus 8 by 2.285 delta omega, approximately 37, that m value. You got the m value. So now parallel with this, that beta is equal to 0.5653. But according to this beta, we know that if a greater than 50, 21 less than equal to a less than 50, and a less than 21, using this all typical value like this, 0.1102 of a minus 8.7 by what you call, and 0.58. It is related to what you call a greater than 50, 21 less than equal to a less than 50. Here we have to use the typical value 0.5842 of a minus 21 or 0.4 plus 0.07886 of a minus 21 and a less than or equal to 21. Here it is 0.00. This, after substituting this all step number 3, right, to observe this typical value, how it is collect this delta and beta and capital M value. Okay, now that h of n is ready to measured. If where alpha is equal to m by 2 is equal to 18.5, and where h of n is equal to sine into omega c of n minus alpha into I naught by pi of n minus a into I naught of beta of 1 minus n minus alpha by alpha whole square whole power of by I naught into b. Okay, the range 0 less than or equal to n less than or equal to less than what you call less than or equal to m. That means here it is. So where right to measure the I naught of u is equal to 1 plus the summation r is equal to 1 to infinity u by 2 of r by r factorial whole power 2. Okay, so with this this is the mathematical analysis of this. So after that, using the piece of code, we are to verify that all response, that h of n is sine into omega c n minus alpha by pi of n minus alpha into I naught of b beta of 1 minus n minus alpha by alpha whole square whole power 1 by 2. Okay, by I naught of b with this 0 less than or equal to n less than or equal to m. With this, the sample versus number of samples versus amplitude. So how it is varies, or the response of this number of samples with amplitude, or what are the main lobe and side lobes, right, to verify. After that, to decide that where it is useful, that Kaiser window design of low pass filter. So whether it's suitable for this either recursive or non-recursive, easily right to compare what is the importance of this particular window, like in a Kaiser window design of a low pass filter. Okay, so here the coming to the relevant to this, the examples of finite impulse response filter designed by the Kaiser window method. The ideal high pass filter with the generalized linear phase, you have to consider this mathematical relation where high pass filter, previously we have seen that a low pass filter. Now we want to consider that high pass filter with what you call e power j omega is equal to 0 at what you call omega mod less than omega c, e power j omega into m by 2 at what you call omega c less than or equal to mod omega less than or equal to pi. Okay, hp of e power j omega is equal to e power j omega m by 2 minus h low pass filter lp of e power j omega. Okay, so with this, so you easily can measure that h of hp of n sin pi, where the sin pi of n minus m by 2 by what you call pi by pi of n minus m by 2. Okay, here also m by 2. So minus, okay, sine into omega c of n minus m by 2. Okay, by pi of n minus m by 2 at minus infinity less than or equal to n less than or equal to infinity. So therefore, where h of n, where it is that h of n, where h of n is equal to what you call h high pass filter of n into omega of n. Okay, this is the what is the ideal high pass filter with generalized linear phase. Okay, so now for the Kaiser window design of the high pass filter, we have to follow the certain specifications. The specifications are available. H and t power j omega mod less than or equal to delta 2, where what do you call that, mod omega less than or equal to omega s. This is one way, and 1 minus delta 1 less than or equal to mod h and t power j omega less than or equal to 1 plus delta 1 at omega p less than or equal to omega less than or equal to pi, where omega s already it is decided, where omega s is equal to here 0.35 pi, omega p is 0.5, delta 1 is equal to delta 21, where it's also equal to delta is equal to 0.021. Okay, so by Kaiser window method, where beta is equal to 2.6, m is equal to 24. In what do you call this particular Kaiser window methodology, we have to consider that where m is equal to 24, where beta is equal to 2.6. Okay, so with this, so after that, try to compare these comments on this recursive or non-recursive. So FIR and IER filter, discrete filter design. If you are using that IER filter, closed form formulas, yes. Generalized linear phase, no. Order is lower order. And coming to this FIR filter, closed form formulas are no, not necessary. Or generalized linear phase is required, yes. Order is high. So where based on this all order, if you are using the IER filter is lower order, if you are using the FIR filter higher order. This is the components on IER and FIR discrete time filter. By using these particular components, you are ready to design according to your task based or maybe your desirability. If you are using any specific response requirement, based on that we have to consider these comments on what you call IER and FIR discrete time filters. Okay, so now with so based on this all analysis, what are the filter realization with rectangular Hanning windows? Okay, so previously we have seen that all what you call Kaiser window and Hamming window also, but especially this case, filter realized with rectangular Hanning window. With this, so this is related to that raised with the rectangular window if that m is equal to 16. Okay, how it is appeared that graphically. Okay, where h of omega and h of e power j omega, how it is varies in amplitude versus the that m value is up to this initial and up to m is equal to 16. Okay, so here we are back to our ideal filter realized with the Hanning window where m is equal to 16. Compare this rectangular window and what you call Hanning window. The m is equal, but it is whatever that all this realized with the Hanning window and realized with the rectangular window. Okay. With this, there are the much less ripple for the Hanning window, but the transition width has increased and compared to this all are. Okay, this is one way. So another filter realized with the Hanning window. Okay, easily right to compare. Improve that somewhat. It is transition width can be improved by increasing the size of Hanning window to m is equal to 40. Previously it is mentioned only what happens where m is equal to 16. Here it is that M value is what do you call that Hanning window is M is equal to 16, and go on increasing that M value 16, 17, 18 up to 20, 25 up to what you call 40. So right, to verify that filter realization with the Hanning window, somewhat it is transition width can be improved by increasing the size of the Hanning window to M is equal to up to 40, from initials to M is equal to 60 to 40. So finally we are right to decide that filter realized with the Hanning windows. Okay, with reference to this, already we have seen the Kaiser window, Dahl-Sebeshi window, and Hamming and rectangular window. So what are the, using these all designs, that our windowing characteristics are reached our task or not, right, to verify that we require that all windows characteristics. So fundamental trade-off between the main lobe width and the side lobe amplitudes. As the window smoother, okay, the peak side lobe decreases. These are the major windows characteristics. But the main lobe width increases. As a window smoother, peak side lobes decreases, but the main lobe width is increases. Okay, so need to increase the window length to achieve the same transition bandwidth. Okay, so what are the specifications necessary for a window design method? So the specifications are, we have to follow these all specifications, where cutoff frequency and maximum passband ripple and transition bandwidth and width of the what you call window main lobe. Okay, so with this response must not enter the shaded regions. That shaded regions usually can analyze. Now there is a key property of the window design method. Okay, we have to consider. Here it is the key property. Property 1 is equal transition bandwidth on the both sides of the ideal cutoff frequency. Okay, with this, and second property, key property of the window design method. So here in this case, using this graphical representation, so the property 2 is peak approximation error in the passband is followed by delta is equal to that in the stop band. This is the key property 2 of the window design methodologies. Now coming to this key property 3 of the window design method. With this, using this all graphical identification, with this property, what do you call a property 3, distance between the approximation error peaks is approximately equal to the width of the main lobe, what do you call delta into omega m. Okay, next here that property 4, with the width of the main lobe is wider than the transition width. Okay, and coming to the key property of 5 of the window design method. So using this all graphical representation. Okay, so the property 5, peak approximation error is determined by the window shape. Okay, the window shape is dependent of the filter order. Okay, here it is based on the order. So directly peak approximation error is determined by the window shape. Okay, now coming to the passband and stopband ripple. Passband, stopband ripple are often expressed in decibels. Passband ripple is equal to 20 into log base 10 of 1 plus delta p into decibels in terms of the decibels, or we can consider that same decibels with peak to peak password ripple is approximately equal to 20 into log base 10 of 1 plus 2 delta p of dB. Yeah, minimum stop band attenuation is equal to minus 20 into log base 10 delta s into decibels, using this all passband, stop band ripples. So we usually can use this example. If the delta p is 6%, but you understand that the 6%, here it is. The peak to peak password ripple is approximately equal to 20 into log base 10 of 1 plus 2 into delta P is equal to 1 decibel. Yeah, coming to the next example where delta S is equal to 0.01. So, I mean, it's, what do you understand this? This is the minimum stop band attenuation is equal to minus 20 into log base 10 delta S is equal to 40 decibel. Okay, the band edge frequencies omega S and omega P are often called corner frequencies. Okay, so one is the corner frequency, and particularly when associated with the specified gain or maybe attenuation. Best example is where gain is equal to minus 3 decibels. Okay, so this is what is the summary of the window design procedure. So after using this all windows like Kaiser window, Dahl-Sevichy window, Gaussian window, and using this all low pass filter and high pass filter and rectangular window and Hamming and Hanning window. After this, so if you want other than this all our specifications are changed, you have to remember this all summary of window design procedures. Okay, first one is ideal frequency response as infinite impulse response. This is the first design procedure. Second one, to be implemented in the practice, it has to be truncated, shifted to the right, or to make it is casual or causal. Third one is truncation is just pre-multiplication by a rectangular window. Okay, truncated, like a truncation. Okay, next the fourth one is the filter of the large order has a narrow transition band. Okay, however, the sharp discontinuity results in side lobe interference independent of the filter's order and shape with the Gibbs phenomena. See, if its order is increasing and decreasing, easy to analyze that order based and shape Gibbs phenomena, how it is reflected. Okay, now the windows with no abrupt discontinuities can be used to reduce Gibbs oscillations. We have to follow this window design procedure. Okay, and then best example already we have seen, but it is popular for using the solar windows with no abrupt discontinuity can be used to reduce Gibbs phenomena. The best or suitable windows are Hamming and Blockman. Okay, so what are the advantages and disadvantages of the windowing technique? So after designing the solar using the windowing technique, what are the merits and demerits? First merit is it is a it is a simple method to implement to get the desired response. Second one is it does not have much flexibility as there are an equal amount of pass band and stop band ripples present in the response that limits the ability of the designer to make the output more ideal. Okay, this is the major thing in for the windowing technique. There is a minimum computation involved in the executing this technique. Okay, so no matter how much we increase the value of M, okay, go on increasing. Just now we have seen that up to that M is equal to 60. Minimum is 16, 40, 30, 20 and so on. So based on that increasing the value of the M, so that what is the response of that window, main lobe or side lobes or all, if it is truncated or whatever it is. Okay, next one, the maximum magnitude of the ripple is fixed except when using the Kaiser window. Okay, because if we are using a windowing technique, we have to concentrate on the Kaiser window. So the maximum magnitude of the ripple is fixed, all other except when using the Kaiser window. Okay, so due to the convolution of the desired frequency response and the spectrum of the windowing function. Okay, so it is not possible to find out the specific values of the pass band and the stop band frequencies. Okay, so when the filter order m is increased, this leads to a narrower frequency response in which the smoothing is reduced. So that's why always we have to use that order of the filter. Okay, so if you are using that windowing methodology, that when the order of the filter m is increases, this leads to a narrower the frequency response in which smoothing is reduced. Okay, this leads to be big side lobes that are coupled with the lower transition width, which is Gibbs phenomena that was previously mentioned, already we have verified. Okay, however, the Blockman window helps to reduce the effects of Gibbs phenomena and keep it to a minimum. Okay, so using this all summary, steps for solving the problems using the windowing methods. You have to numerically and graphically using the software or hardware or whatever it is. You have to follow these all steps for solving the problems using the windowing method. Let us look at how to utilize these functions that we have to learn about in a problem. Okay, first let us go through the steps to solving the problem relating to the windowing method of finite impulse response filter. So the distal FR filter. So these steps you have to follow. Okay, step 1. So find out that h of omega and omega c of h of omega is equal to e power minus j alpha omega. The equation can be given directly in the equation. Okay, so the value of m can be given and you have to calculate that alpha is equal to m minus 1 by 2. The phase delay is given. The value of alpha with which you can find out h of omega. Okay, here this value can be given directly. Okay, so the cutoff frequency fc can be given with which you have to find where that omega c is equal to 2 pi into fc. The sampling frequency fs can be given with which you have to find omega c is equal to 2 pi fc by fs. Okay, this is the step 1. Yeah, coming to the step 2. Now we find the value of h of n of the IER filter impulse invariant IER filter response by taking the inverse discrete Fourier transform of h of omega is what you call less than or equal to what you call LP. Okay, with the letter that h of n is equal to, here it is where h of n is equal to what you call 1 by 2 pi integral minus pi what you call 2 pi, so h of omega into e power j omega n into d omega. Okay, so after that try to calculate that for a low pass. If you are considering low pass filter, so now that try to calculate that where h of n is equal to 1 by n of n minus a. Okay, n minus a into what you call sine of n minus alpha into omega c, the cutoff frequency. If you are using the different filters or high pass filters, what you call for high pass filter, we have to follow this one, and we will have to find h of n for all values of n based on m, however when n is equal to alpha. Okay, so like this, hence the what you call integral term will be cancelled off if you are following this all on. Okay, so like this, you have to analyze this all windowing techniques using the different filter or whatever it is. Okay, thank you.
Like, share and subscribe. hit the bell icon for more updates.